this series, we are focusing we are trying to build up on this topic. Our session today is titled Get Up to Speed with Wolfram Tools for LLMs, and then we'll follow up with the sessions from neural networks to large language models. Then we have a session titled Playing with LLMs in Wolfram Language, and we'll end with a Q&A session with Wolfram experts coming up in a few weeks on May 24th. Our focus for today's session is really a part of the toolkit available from Wolfram for working with AIs. Wolfram has a number of different tools available to work with AIs. Just released Wolfram plugin for ChatGPT Plus, which is pretty amazing to work with. Wolfram, you recently concluded a session, a week-long session, daily study group series where we talked about this. We investigated, worked through many different examples, and then we have lots of other tools, API for building real-time APIs for AIs. But today our focus really is on this segment of the toolkit. Basically, the language itself, the symbolic programming language that Wolfram Language is, and the machine learning framework that is available, specifically the neural nets framework that we have available. My outline for today, I'll start with a very quick, very brief review of some Wolfram language syntax, especially to help our beginner users come up to speed so we are all on the same page, and you are not you're not left wondering about some of these characters and function names that you see on screen. And then we will get into machine learning right away. We'll start out with some interesting examples of built-in machine learning that's available immediately as you start using the language, but actually have neural net models running under the hood there. So you're able to take advantage without actually coding yourself. Then we'll move on to the neural net framework. I will talk to you a little bit about building blocks of neural nets, and then how you could use them to build and train your own models, and the options for using existing neural net architectures. So I must admit, the webinar series is titled Learning About LLMs. Our session today is not going to talk as much about LLMs. Our hope was, with this session as a primer, we allow all of our attendees to, get on the same page, so that in the upcoming sessions where we have our developers, Julia Alessandrini and Geoffrey Spiegel-Pons, talking to you about LLMs, you have the tools you need to work with those models, to play around with them on your own, to be able to, work with them in Wolfram notebooks using Wolfram language code. So I hope you're not disappointed that we are not going to talk as much about LLMs in this session itself. I promise you the fun stuff, the more interesting stuff is coming, but I hope this session you find it useful as we talk about the tools that you can use. So let's start quickly with Wolfram language syntax. I try to time myself here. I'll try to finish this up quickly in a few minutes so we can get to the more interesting parts. So for our beginners especially, just some quick information. In Wolfram language, the way you go about assigning a value to a symbol is very much like other programming languages. If I want to assign the value 7 to x, I just say x equals 7, and now x has a value 7. So if I go ahead and use it in further calculations, the value is used. This is what is known as immediate assignment. In Wolfram language, you also have what is known as delayed assignment, where we make the assignment, but the value is recomputed every time it is needed. The value is not computed right away, but only kind of just in time when it is needed. So for example, here, I evaluated this statement and you see nothing happened here. Just that the assignment was made that, okay, if I use t later on, it should reevaluate now, which gives the current time, and show it to me when I use t. So as you noted, I evaluated it a while back, and now I'll go ahead and evaluate, and I see, okay, it gives me the time right now. And again, I've been speaking for a little while, so if I go ahead and try a little later, you see the difference here. This was 13:10:43, 13:10:53. And so with delayed assignment, you can make an assignment, but then the right hand side will be recomputed every time you use the left hand side. Okay. You can clear away by any assignments using clear here. So now you see the color change here, the syntax coloring that shows that now X and T have no assignments associated with them. I cleared them out. Immediate assignment is most often used in, you will see it used in one specific case most often, that is for function definitions. And this is how you go about defining a function in Wolfram language. This is the name of your function and you provide the input arguments. You do have to provide this underscore here right next to the name of your argument, because we provide them as patterns. The underscore stands for what is known as a blank in Wolfram language. The idea is I'm setting up a pattern. So when later on I use the function, whatever I provide within the square bracket, they will match the pattern that I've set up the function definition to expect. And once that pattern match is found, those matches will be used on the right hand side to do whatever I want the function to do. Okay, so here I have a very simple function, accepts two arguments. You see I've set them up as patterns, and then on the right hand side I use those and I provide sort of transformation rules to work with those pattern matches. As this was a delayed assignment, you saw nothing really happen. That assignment was stored away. And now if I use the definition with two arguments, 4 and a, it does what I asked it to do on the right hand side. It adds 4 and a. I can go ahead and clear the definition again. Now in Wolfram language, you can go ahead and use immediate assignment for very specific definitions, right? For very specific input values. So I am defining that f of 1 will always be 2. There's no ambiguity here. I know I will be asking for f of 1. So I can go ahead and use immediate assignment here and here. And now later on, if I try to use f on other inputs, the ones that do not have any assignment associated will just be left untransformed. And it's going to be a symbolic function. It is left as a symbolic expression. The system just doesn't know what to do with an f of 4 right now. And if I do happen to set up a different definition later on, it will be able to do that. Okay, so I'm going to go ahead and define provide two other definitions. One for integers, where my input matches the pattern that it is an integer, or my input matches the pattern it's a string. So Wolfram language does not have types as such. So if you're coming from a different language and have been using types, we do not have that in Wolfram language. Everything is a symbolic expression. However, a symbolic expression has something known as a head, and that head can be used for a kind of generalized type designator. So with the help of the head, I can figure out, oh, is this an integer or is it a string? And I can have different definitions so that it works differently depending what sort of input I provide. So for f of 2, now it gives me x plus 1, gives me 4. And then if I have a string, it behaves differently. Now, a lot of times, as you see the code in our following presentations and a lot of other places, you will notice these characters strewn about in the code, and sometimes newcomers get a little confused. What is this about? These are just different notations for applying functions to the argument. This is the standard notation. You have the function name, square brackets, and the argument within square brackets. And you can also provide it with the prefix notation, where you say the function name at and the input argument. It does the exact same thing. Sometimes if you have, you think of a function that you want to apply to an argument as kind of an afterthought. So you already, did something. Maybe you counted the number of times an element occurs in a list, and you have that, and then you realize, oh, you know what, I should have sorted it. So you want to tack on this second function as sort of an afterthought. You use the postfix notation. And again, it does the exact same thing. So all of these three options, they do the same thing. It's just what is more intuitive for you, how you want to use that function. Um, Okay, now we mentioned that everything is a symbolic expression in Wolfram language. So whether it's a number, a string, a list, all the way to a full-fledged neural net model, they are all represented, in this consistent way that really that makes the language so powerful. There's this uniformity in which you can deal with different types of things in Wolfram language, and you can work with them. And let's take apart, let's spend very little time in this the structure of a symbolic expression, and hopefully that makes things clearer, especially when you're working with neural nets later on, that kind of follow this that actually do follow the same structure of a symbolic expression. So they have the same fundamental structure. They have a head. Each expression has a head, and then within square brackets you have arguments. Now this head can represent, the type of the symbolic expression. In this case, it's a list. It can represent an operation, in this case plus. It can express, again, represent what type of an object. In this case, we have a graphics, 3D, and so on. Now, what's beautiful about Wolfram language is that it's fully symbolic. So undefined, so-called undefined variables can just stand for themselves. I can just have an X, and I can continue to work with X symbolically. I do not have to have a defined value for X. Um, you saw the structure of the expression, right? Now it has multiple parts, and you are able to access any part of an expression. And the parts are indexed starting at 1, and their shorthand notation is the double square brackets. It's slightly different. So the single square bracket is associated with a function. The double square bracket allows you to index into an expression and extract its part. So for example, I have an expression which is a list here, and I want to get its second part, so I can go ahead and get the second part of the expression in this way, or I can use the shorthand, the double square bracket notation, and get the second part in this way. I can use negative indices from the end, and then I have lots of different options. I can span, and so on, but I will not get into the details. I do want to point out, at any point, if you have any questions, newcomers, I always encourage people to look up documentation. So you hover over a function and you click on the eye, it will take you to the documentation about that function. And there you will find lots of examples that explain how and where to use this function. You have details that show you all the different options that can go in there, and you can just learn more about using this particular function. So we can have a nested expression, and you can use the part function to get to different parts of the nested expression. So I'm getting to the second part of the full expression. And how do I know that is the second part of the second part? I can actually look at the full form of the expression, or I can also look at what is known as the tree form of the expression, that shows the expression tree, and so I know this is the second part, and then the second part of the second part is 2 plus d. So that's how I get to that part of the expression. um, y- your data often comes in as lists when you're trying to do machine learning. And so it's helpful to know a little bit about working with lists. A list is an expression, and so part function works just fine, as you saw. But there are also a bunch of dedicated functions that can be used on lists. So as the name suggests, if you have, you want to get the first element of the list, you can use first. To get the last element, you can use last. You can take the first n elements using take, and you specify which n elements you want, or you can drop the first n elements and have the rest, or you can do both of them together and get two lists using the helpful take drop. Why did I bring up these functions? So it's easy to see how they work on on simple lists, and then later on you will see that they have kind of similar functions available in the neural net framework that will allow you to symbolically work with neural net models in pretty much the same fashion that we've been working with lists here. And I hope the names then give you an idea based on what you saw. What we did with the list, the names will give you an idea how you can work with the neural net model in a similar way. A few more interesting things to keep in mind as you work with Wolfram language. The way you apply a function to an argument, you've seen that you name the function and then within square brackets you provide the argument. The argument can be any symbolic expression, an image, text, string, numbers, anything that's a valid Wolfram language expression. Now, some functions automatically come with the listable attribute, which means they work on a single element, single argument. They work on a list of arguments. So instead of trying to find the log of a list, which doesn't make sense, log is listable. So it knows, oh, I need to find the log of each of the elements in the list. Now, you might have a function which might actually work on a single element as well as a list of element, in that, like, it can actually use an entire list as its input. So how do you make that function now work on the individual elements of the list instead of the entire list? So then what you want to do is you want to map the function. So I'm going to map the function f over the list so that it actually works on the individual elements of the list and not the entire list. And so now I have mapped f over each element of the list. Because map is just used so often in so many different places, we have this handy shortcut, which is the /@ the short notation. And you can say f/@ ABCD, and it will do the same thing as we saw here. So here's a quick example that shows, see, if framed works just fine on a list, right? So it doesn't know that you wanted to frame each element of the list. It'll just go and put a nice frame on the entire list. But when I say framed /@ elements /@ the list, then it knows, okay, I need to frame each individual element. Okay, we are wrapping up our quick review, blinding fast review of some of the important um, elements of using Wolfram language for programming. We'll end with our handy functions for importing and exporting. Wolfram language automatically handles hundreds of data formats and subformats. So if you're looking to import some data file for your model, you can just go ahead and use import. If you provide the name of the file with the path on your local system, you can go ahead and import it that way. You can provide the URL to the file if it's available on the web, and you can import it that way. You can also use export to export anything. So if you have created some data, you can export it to a CSV file, XLS, any format of your choice. And we have all those listings again available in our documentation. You can find a listing of formats that will tell you the basic formats that are allowed for import and export. What I thought would be helpful for this session is showing you that you can export to the WLNet format, which is Wolfram's format for storing neural net models. So if I create a really, really basic model here, I can go ahead and export it, and this will export my model to this format. You can also export to the MXNet format, so for example, again, if I go back to the documentation here, let's see, I already had it open. Oh, maybe I didn't. So I'm going to open it up again. And we looked at WLNet, which is for storing trained and untrained neural nets in Wolfram's native format. And then we also have, you should also be able to export models and import models from MXNet format. Okay, great. Now, in a few minutes, let me show you some examples of built-in machine learning in Wolfram language itself. So a few years back, we started off with the image identify function. It was a lot of fun to work with it. I have some examples here of image identify working on input images, giving you what it thinks is the main content of the image. So I won't go through each of those examples. You have access to the notebook. I would encourage you to go ahead and try those examples. There's also a bunch of examples that show you other image processing functionality. All of these are actually using neural net models under the hood. So they're pretty powerful. Image contents here identifies entities present in an image. A variation image contains Q can tell you whether or not that image has a specific entity, or it can tell you whether this image is an instance of a given category. And some more fun functions like, image restyle, which will restyle an image in another style. So these are all pretty fun examples, but I will not linger too much here. Let me show you a few examples. So I have examples from both text processing and audio processing here. Let me show you a few examples of text processing. So for example, here, because you will be working with a lot of text in the future sessions. So we have a few powerful text processing functions built into the language itself. There's text sentences, which can take a piece of text and extract all the sentences. So here I'm going to extract all the sentences from the Declaration of Independence, which is actually available as example data built into the language. So it's pulling out all the sentences here, and because I had a quick function length to find the length of the list of sentences there, I can see there are 35 uh, fragments that are considered as sentences in this bit here. We see that towards the end, it's not quite sentences, like the signatories, and that fragment is considered as a sentence. Beyond sentences, I can also get words from a sentence or a piece of text. I see that this sentence has 71 words. I use a text words function. There is a text cases function, which can identify all cases of text identified as a specific type. Now, this type can be a part of speech, like, a grammatical entity. In this case, I'm getting all the nouns. And you can see, which noun is most often mentioned in the Declaration of Independence. And then I can also ask for a specific type. I can ask for countries. So in this example, I'm pulling in the data on rice from Wikipedia, and I'm trying to identify all the instances of countries. And with a little bit of code, a little bit of instruction, I can tell Wolfram language to not only identify the country, but get them out as Wolfram language entities so that I can work with them later. So it pulls out the country, the mentions of the countries as country entity. And, sometimes there are the names of countries that are not quite interpretable. So I've just instructed that, it should verify the interpretation that indeed there is a country, and the Wolfram language recognizes that entity as a country. And once I have extracted all those countries from the article on rice, I can see, I can do a quick count to see how many times each country is mentioned in the article. And based on the number of times it is mentioned in this list, I can have a quick geographic visualization. Um, Beyond this, there are other built-in functions that are very sophisticated. So there's find textual answer, which when given a piece of text and a question relevant to the piece of text, will use this text to find an answer to the question. So once I have given it a piece of text like this, that Paris is the capital and most populous city of France with a 2015 population of so and so. If I ask the question, how many people live in Paris, it's able to give that answer and tells me where in the text that answer occurs. And it is also able to answer this question, in which country is Paris? Um, And my last example for text processing is this one here. You see, I have a list of animals and a list of fruits. I'm going to put that list together and I'm going to create a feature space plot. Feature space plot is a Wolfram language function that allows you to quickly visualize the data in feature space. And now you see I have a bit of a mess here because I've just given it a bunch of strings. The regular two-dimensional clustering is trying to place words together based on their distance from each other, which is not really semantic distance, right? So it doesn't know the meaning of the words. It's just putting things together, that's kind of have the same characters and so on. But I can go ahead and use a neural net model that is actually trained on um, using meanings of words instead. And so I have the same function, feature space plot, but I instruct that it use a special feature extractor, which is a neural net model. And so hopefully it is now able to distinguish between the animals and the fruits and present a better clustering in terms of meanings of the word. So I hope to get the fruits in one cluster and I hope to get the animals in the other cluster. So if you go ahead and try this code in the notebook that you have downloaded, you will often see this little blue box that you see on my screen right now. A lot of these models are actually available in the repository and they are not provided as part of the language itself when you go ahead and install Mathematica or Wolfram Desktop on your system. But when you go ahead and use these functions, it tries to download that model. So it might take a little time, but once that model is downloaded, it is able to use it and it will perform the computation and then give you the results uh, in the notebook itself. Um, and so here's what it looks like right now. So we have had a better cluster here of the fruits and the animals. And notice this interesting cluster here with the apple and the blackberry. And I'm sure you're getting why these have been put in this special cluster here. I won't go through the audio processing examples, but I hope you have fun trying them on your own. I want to really cover this section, which is really, really important to prepare you for the next two sessions coming up. So just for some of our attendees who are brand new to neural nets, I wanted to go over this quick review so that we are all on the same page of what we are expecting out of neural nets. Um, we've heard this probably already, that the neural nets are kind of inspired by neurons. They're not exactly recreating what neurons are done, but the setup was inspired by neurons. And now currently neural nets are capable of machine learning from examples, any type of inputs, images, audio, text, numbers, videos, and so on. What a neural net really does is kind of develop a function that maps the input data to some sort of an output, and it does so by recognizing patterns in the data. At this point, I will point out that we shared with you a link to Stephen Wolfram's blog post about what is ChatGPT doing and why does it work, which has been reviewed by Sam Altman, the CEO of OpenAI, as kind of one of the best examples of best explanations of what ChatGPT is doing. So anyway, I very much recommend, if you're new to neural networks, to read the Stevens blog post. It starts at zero levels, no prerequisite, no requirements of having known anything, and it's just amazing how easy it is to understand what is going on the way he explains it. And so if you're curious about, if you're starting from ground zero, it would be, this is a great resource to understand how not just ChatGPT or an LLM works, but basics of how the neural nets work. Okay, so back here, There are certain building blocks you need to build an neural network. You need encoders and decoders because neural networks work on numeric tensors, and you have all different types of data, images, audio, text. You need to convert those to numeric tensors, and so you need these encoders that convert from other data type to numbers, and decoders that convert from numbers to the kind of output you want. Then you want layers which will perform mathematical operations on these numeric tensors. And these layers will be connected in many different ways depending on the applications. And so then you have containers which allow you to put the layers together in a sensible way. Now, the network can have an input layer, as you see here, and can have an output layer, and in between you will have hidden layers. The depth in the deep neural network refers to these numbers of hidden layers in there. The way a network goes about learning is what is also known as training. What it is really doing is an optimization of the model parameters, and it does it iteratively. There are well-established algorithms that allow a neural network to do this sort of training, namely stochastic gradient descent and backpropagation. There are different types of neural networks. The multi-layer perceptron is the simplest neural network, and we might take a look at one just as to figure out how we can put things together using the Wolfram neural net framework. We know now that convolutional neural networks are great for recognizing images. Long short-term memory neural networks are great for speech recognition. Large language models, the focus of this series, is great for understanding, summarizing, and generating text. So now let's get into the Wolfram neural net framework. As our CEO and founder mentioned, that the entire system is symbolic, very much in keeping with the symbolic nature of Wolfram language. So the neural nets in Wolfram language are computable. They are symbolic constructs, and they can be programmatically manipulated, visualized, and so on. We have built-in encoders and decoders available, so you don't have to write your own to convert your input to numerical arrays or convert numerical arrays to output. We have lots and lots of layers available to help you process the tensors. We have different types of activation functions, loss functions available. We have different ways, what we call containers, to put together these layers and build chains and graphs of the layers to build your network. And then, of course, this the main algorithms, they are built in backpropagation or stochastic gradient descent. So you don't have to worry about writing or building that into your model. And then we have also options to run your model, train your model on optimized hardware. These options are available. Let's take a look at some encoders and decoders available in the language. So for example, say my data has two classes. And I want to kind of maybe build a classifier that classifies my samples as male and female. These are just my classes available. So I can quickly create an encoder using net encoder. Right, this is my net encoder, and so its name is ENC. And then when I give it these class labels, male or female, it will quickly give me an encoder. So basically what it is doing, as you see here, it recognized that there are two classes, and it just gave the number 1 and 2, 1 for male, 2 for female. So yeah, is it difficult to write code that will do the same? No, it's not. But it's even more easier when you have a built-in function that will do this for you, because this can quickly morph into something a lot more complicated. Similarly, I can build the decoder. So if I'm given this class, I can decode it into numbers. So if I'm given some numbers, I can decode it into this class. So if I end up with these numerical outputs from the last layer of my neural net, I can quickly decode that into the class male and female. I have some other examples. This is the encoder for an image. So we have a number of encoders identified just by the type of input it can encode. So we have audio encoders, characters, image encoders, tokens, and video frames. So if I have to deal with images, then I can just go ahead and use the ImageNet encoder, and you can see that it immediately creates this 3 by 128 by 128 tensor of numbers that represent that image. And do the um, if I apply a net decoder that's an image, then I can work on that same output and get back my image. Okay, so encoders and decoders are very important at the beginning and end of the network, but all the main action is happening in between, right, in the layers. So we have a huge number of layers. Here's a quick listing that you can see. The most common types of neural net layers that are used in models today that are all available, and there is individual documentation pages dedicated to each of these layers, and there you can also find a guide page on documentation that's just dedicated neural net layers, and you have them categorized by basic layers, custom layers, and so on. So quite a collection that you can explore here. And having the layers is great, but we saw that we have to put the layers together. So we have two main containers available in Wolfram language. We have the net chain that just can create a chain of layers. So this is just a single layer chain. I have just one single layer, and that's it, nothing else. So I can put that in my net chain, right? Or I can string together a number of different layers. These numbers actually represent linear layers, because linear layers are used so often. You can actually replace this whole thing, linear layer, and the number of nodes in there with just the number n here. So I can string together 5 different layers in one chain, and this is what it looks like. And I can open it up, and you can see this is my network model. It takes an input. I have the first linear layer, then I have the tanh layer, I have the linear layer, ramp, linear layer, and the output. And note that it says here in red, uninitialized. So that tells me that this I have put together a net, great, but it is uninitialized. So the weights and biases have not been initialized in this network. A graph is really an option to connect together layers in any topology, like put together a graphical network. A really simple graph would be uh, a, a chain really here. But here's another example where you see I have connected layer 1 to 2, 2 to 3, but then I've also connected 1 to 3, and then 3 to 4, and I've connected 2 to 4. And you can see this here. You see the net graph that has been created. And so you can nest different types of containers. So I have a chain here. First, I create a chain. This is a basic chain. And then I can embed the chain within the graph. So I have a graph here that has one layer, and then I embed the chain within the layer, and I provide information how they are to be connected. Okay. And then I can have input and output ports. I can say that my graph needs an input and output port that will be added here to my model. This adds an input and an input port. I can also call these. I can have specific names for these ports. So see here, I have the input port, I have the output port, and I have a separate port that I call sum. Okay, I know I'm going really fast. We are short on time. I have 1 hour to prepare you for the next two sessions. So I want to put out there all the resources available, the functions that you might be interested in. At the end of this notebook, there is a references section which points you to further resources. As I mentioned, Stephen Wolfram's blog post is a great place to start. And then we have full-fledged tutorials in Wolfram language in the documentation that will take you and handhold you through examples and show you exactly how to utilize the functions. So that is a great place to go in and try the different functions and try to work with an example neural net available in that tutorial, or put together your own and work with those. So if this is new to you, hang in there. Just we will have a link to the recording available. You have the notebook available. You have all these different resources available. Take your time, go back and review and see. Try to identify the functions that are of special interest to you, and bring back your questions to us. We have another session coming up on Wednesday, and we'll be happy to take your questions then as well. We will have experts from our development team to answer those questions, and hopefully we can get you started working with neural nets on your own, and further on working with LLMs as well. Okay, so let's see. Um, Remember when we created a very simple linear layer, you see that it says this in nice bright red, it says uninitialized. It's trying to warn you that while there are parameters there, weights and biases, they are in red. That means this network is untrained. It has no meanings. This is kind of like you've put together a piano, but you have not tuned it. So now if you go and hit the keys, what you will hear is not quite what you expect to hear from a piano, right? So initialization is kind of like the piano tuning process. So now if I go ahead and tune my piano, I have initialized the weights and biases in the network. Now, will it do the job? Not yet, because remember, the reason a neural net works is because it has been given examples. It tries to learn patterns from examples. So it's not sufficient to just initialize the network. You also need to train it. But once I have initialized it, these weights and biases are given some random numbers. So I can actually extract the values of those parameters using specific functions. So I can use weights, the option weights, to get the weights out of the network. You will see that this is a numeric array. Its dimension is 2 cross 5. And I can also get the biases out of the network. And you see it's a two-dimensional. So I think I had just two. Let's go back here. Yeah, I had two nodes here. So it has two biases, associated biases. Okay, so in this remaining part of the notebook here are a couple of simple examples, a very simple linear layer. So for example, if I had just this data and I wanted to create a linear layer of size 2, and then I tell it that yes, in the input you can expect a tensor that has 3 elements, right? Oops, I need to provide the data as well. And I can extract the weights. And let's see, here is the output of applying that layer to the data. So what is it doing? It's multiplying the weights with the input, the dot product of the weights, and then adding the bias, and then that's what I get. And I can recreate that same mathematical function using my own function. Here's my data, here's the weight, here's the bias. So I'll get a dot product of the weight with the data, add the bias, and give you the results. So I can go ahead and do that here. Let me define my function. I'm extracting the weights from the neural network. I'm extracting the biases, and then I can do the calculation using weights and biases. That seems like a completely useless operation, right? I mean, I have the layer doing it. Why did I go about setting up a function? Purely for demonstrative purposes, purely to show this is what is happening in here. Like, if you had to write the code from scratch, then you would have had to, written something like this. But here within the framework, you have all these layers that are doing these mathematical operations for you. And so you can focus on just building the architecture of the network, or working at with the network at a much higher level, at a symbolic level. Okay, now beyond that simple example, there are two other examples. Here's one that builds a convolutional neural net. We know they are good for images. Um, there's actually a really fun example here, but unfortunately, oh no, it's not here. Further on. There's another example here where there's enough. The creator of this example, it's not me, whoever created it, one of our authors, one of our developers from the machine learning team, they were kind enough to provide extensive comments that explain how this particular network is built and what each layer is doing, why it is important, and so on. So I hope you are able to go through these examples on your own. I want to spend the last few minutes on showcasing some of the other resources that are available for you to work with neural nets using Wolfram Language. I think one of the most important resources we have available is the Wolfram Neural Net repository, which is a collection of trained and untrained neural nets, and you can go ahead and explore the repository. The models are categorized by input domains, whether you're working with audio data, image data, numeric text, or video data, or you are interested in a specific kind of task. You are looking at classification or language modeling, and here you have all the models available. And the way you work with these models is you go to the page in the neural net repository for this particular model, and in the examples section you will have code that shows you how you can download this model. For example, you can just go ahead and copy this bit of code here, open up your notebook, paste it in there, and evaluate, and you now have the net model downloaded and ready to use on your system. Let's go back to the neural net repository. It will then show you other examples how to get at the model parameters, some examples that show you the basic usage for this particular model, maybe a little bit, since this is a transformer model, a little bit about the transformer architecture here, and other metadata, some external links about the actual paper which this model comes from, and so on. So the repository again is a great resource. I hope you're able to use that. There are models from other frameworks, and also lots and lots of models trained by Wolfram Research themselves. So shall we do this example? Let's see. uh, Yes, we should, because it's just so much fun. So this is really the Wolfram's model. This is the earlier version of the neural net model that is powers our image identify function. Such a simply named function, but incredibly powerful. So first we'll go about downloading the model. It is pre-trained, so we don't really have to do any training. And you see, whoa, you see all the layers in there. And then you can get some other information from the model. So uh, I think I skipped that part, but I can show you quickly that with the help of the information function, you can always get further information about your model. It will summarize the information there, and you can see, you can understand a little more about your model. But the more fun part is actually using the model, right? So we'll go ahead and use this model on this image of a peacock here. And the way it has been set up, this model, that its output is not just a class label, but it is actually a Wolfram language entity, and it's very specific at that. It says it doesn't say it's just a peacock. It says it's a blue peafowl. And you can look at various properties of the predicted entity. You can look at its definition, its other properties, and you can also get its top 10 predictions. So instead of just getting the top prediction, you can see that, it was most confident it was a blue peafowl. It was wondering if it might have been a green peafowl. It's definitely a peacock. And then, with less and less probability, we have some more interesting results here, which thankfully were discarded in favor of the more probable result here. Sometimes it might come across an image that it has not encountered in training, and then it'll try to make the best guess in that case. So how do you go about using these models available in the repository? You download the model. Okay, as I said, you look at information. You can also look at these specific properties like the summary graphic, which shows you how really this particular model was created, and you can see, how here's a convolution layer, and how all the different layers were strung together. This is an untrained model because you see this uninitialized here. That's telling you that it's an untrained model, an untuned piano. You won't be able to use it, right? So you can go ahead and initialize it, but with initialization, you just have random weights and biases, and so you can expect garbage output there too. But you can download your own training data. And once you've downloaded training data, Linet is a famous model that was created to um, identify digits from images of handwritten digits. So I fed it an image of a 0 and it failed miserably. I can go ahead and train it on training data available. The MNIST dataset has 60,000 training images. I won't let it train for so long on 60,000 training images. I'm going to stop it pretty soon. But the interesting thing is, even when I kind of stop the training, you already see the loss function has reduced drastically. And so I'm going to go ahead and stop it. And if I use however it has been trained, I get a decent answer right now when I feed it in a new image. Um, so with the Wolfram Language neural net framework, you have all these interesting functions that are available to kind of extract different parts of the layer and reconnect them if you choose to. So here's the trained Linnet that we just saw in the previous example. I can go ahead and extract the very last layer from this neural net model. So this is the layer, this is a softmax layer as I can see, and I can see what it does when given a set of inputs. Now I can see that it is expecting an input vector of size 10, so I give it an input vector of size 10, and I can see what sort of an output I get. I get an output vector of size 10 as well, and because it's a softmax layer, I know it should sum up to 1 because it gives kind of probabilities that should sum up to 1. Now, this gives you an idea how you can really take apart the symbolic representation of a neural network. So here's another version of the image identify net. If I try it on a sample image, I can see it works great. It recognizes this is an image of a tiger. Now I can extract the first 5 layers of the net. I'm using net take in this case. Remember take, drop, take, drop that we used on the list. Here's net take that will work as easily on a fully formed neural net model. So this will give me the first 5 layers of the network. And I can see I have the 5 layers here. And now I can see what happens when I apply just those 5 layers to the tiger image. Now I get a whole bunch of numbers. Where's the fun in that? I'm going to try and make images out of those arrays of numbers. And then I can see this is what the model is seeing at the end of the 5th layer. These are different parts of the images that it has identified at the end of that 5th layer. So here's another example that is looking at this image of broccoli at the end of the 10th layer. Very, very interesting. Now, what happens if I kind of drop one of those layers? I'm going to drop the 6th layer. So I'm going to take the first 5 layers, and then I'm going to take the layers from 7 on. So I'm going to drop everything up to 7. So basically, I'm just dropping the 6th layer. putting it back together, making a modified neural net. And then I am going to use, this is the original net, remember, as just the one that I had downloaded. It gets it. It's sprouting broccoli, it says. And then I drop the sixth layer, and I have handicapped that net a little bit, and apparently it now thinks this is an image of salt shaker. And so we see that sixth layer seems to be incredibly important for this particular neural net model to work well. I'm going to end the session, but I'm just going to share a quick thought. Sometimes a very relevant question that arises at the end of a session like this was, okay, great, you showed me that, okay, the sixth layer was important. You showed me how I can put together layers to create a particular kind of a network, but how do I go about figuring out what architecture to use? How do I go about figuring out how should I connect the layers? And as you will, and you will note, even in his blog post, Stephen Wolfram says it's very much an art still, how different architectures are put together, how networks are connected. Of course, it has been established that certain architectures do well for certain tasks. So over mm, periods of time, trial and error, seeing the results, we have figured out, yes, certain models work well. But right now, especially for beginners, I think it's okay not to worry about how to put things together. There are a ton of models out there for you to use. Our repository itself is a great source for these neural net models. You can download and work with these models. And there is this interesting term used in the community, which is called net surgery, which is a term used for the idea of taking an existing model and then performing surgery on it, adding layers, selecting, combining subgraphs, modifying it, kind of along the lines of what we did with the neural net to, make it identify broccoli as salt shaker. So you can do these neural network operations and modify the net and then retrain it on your own data. So you don't have to worry about building it from scratch, building the neural net model from scratch. Start out with an existing model and then use all these handy tools that you have available in the Wolfram neural net framework, and then you can retrain it on maybe your own data. I have a fun example here that kind of retrains the ImageNet, the image identify neural net model from Wolfram, and retrains it on a very simple toy data set of old movie posters labeled as from the genre science fiction or comedy. And then it retrains that model and tries to use it to identify new examples as whether they are science fiction or comedy. All right, so as promised, here are the references for the absolute newcomers to the world of neural networks. This is an interesting video that was created by Olivia Walsh for Wolfram Outreach team to help people understand pretty easily what neural networks are doing. We have a tutorial collection in our documentation center. As I mentioned, it takes you step by step through uh, what you need to build and work with your own neural net framework. We, of course, looked at the neural net repository, a great collection of models, both trained and untrained. We have a couple of blog posts that go along with the neural net repository and hopefully will help you understand how best to leverage what the neural net repository has it makes available. And then, of course, we have our page dedicated to Wolfram Tools for AIs. You'll find interesting information here. Right. Thank you so much for attending the session today. We hope to see you next Wednesday with the really interesting stuff as we move from neural net models to LLMs.